Okay, just a little more. If you add two vectors in a plane, you get another vector in the plane. And if a vector isn't in the plane, you can't get it by adding vectors that are in the plane. That's pretty much a characterization of what it means to be a subspace or a space. Okay? The plane forms a space within three-dimensional space. We do call it a subspace, but it's a space in its own right. Now, that's not quite a precise statement. If I say if you add multiples of two vectors in a plane, you get another vector in the plane. And you can't get a vector in the plane by adding multiples of other vectors in the plane. A vector that's not in the plane by adding multiples of vectors in the plane. You really get something that's very close to a good definition of a space. Matter of fact, pretty much all you need is this, because this would follow from this. If I said multiples of the two vectors, add multiples of the two vectors. So, very interesting, very powerful idea, and it's not confined to do two-dimensional spaces, planes in three-dimensional space. We can go to any dimension and talk about what we call hyperplanes, and we can do all the mathematical manipulations. The only thing we can't do, if we go beyond three dimensions, we can't visualize them. Now there's even more, because vectors aren't only vectors in space, okay? And there are vector spaces of functions. There are vector spaces of specific types of functions, polynomials, classes of trigonometric functions. And those really aren't that difficult to deal with once you have the idea of vectors that you can visualize in space. And we're going to talk a little bit about that now. You want a more advanced course, we get very deeply into that topic. If you get really interested, I'll talk about it all day. But the whole point now is that anything we can do in two or three dimensions, and you get some idea of how working in three dimensions is no different than working in two dimensions, except now you have three numbers for each vector. And your matrices have to be bigger. And if you go to 4, 5, 6, 12, 48 dimensions, obviously your vectors get longer and your matrices get a lot bigger. And you got to do a whole lot more work, but there are ways to do that efficiently. Okay, well, that's kind of the idea. I don't want to talk too much more about that, because we want to get experienced at drawing and visualizing these things before we talk too specifically. Okay, well, that kind of completes an overview of a linear algebra course, of this linear algebra course. There are things that we're going to do that I haven't mentioned, but this is a really, I think, pretty relatively complete core of ideas that we're going to build on and develop throughout the course.